In this video, I'm going to talk about the displacement current and the more general form of Ampere's law, and this is in chapter 31-7 of the textbook. Okay, so as it turns out, Ampere's law, the way we've written it, actually has a problem. So, of course, Ampere's law, if it's really a law, should work regardless of how you pick the surface of the loop. And we can see it fails in a particular way. So you could look at charging a capacitor. So that's the situation over here on the right. So we've got a wire coming in carrying a current, charges up the one side of the capacitor, sets up the electric field, so you get an opposite charge on the other side of the capacitor and a current going out. So let's say we wanted to find the magnetic field at point P right here, and so we're actually going to define the Amperian loop like the loop in orange right here. So in principle we could do that, and what we would find is that the current, as the surface we took the little light orange here, what we would find is that there's a current I, which is a real current going through the wire. But the problem is it shouldn't actually matter how we choose the area for this loop. So for example, we could have just as easily, right, so here's the same exact Amperian loop, but now for the area, it bulges down until it goes through the center of this capacitor. And then the problem then becomes that if you look at this situation, well, since there isn't actually any real charge going across the capacitor, then we would get zero current in this case. So it would give us a different answer, and that's a problem. And the issue actually comes because we've now gone beyond what's called magnetostatics. So the current is changing, so the electric field is changing, so things are changing, and that's what causes the problem here. So Maxwell actually figured out how to fix this up, and what he did is he added a term to Ampere's law that depended on the time derivative of the electric flux, right? So now things are changing, the flux is changing, and so he adds this flux term. So now the first part, so the left-hand side, right, is just the Ampere's law, right? So you're calculating the path integral around some closed Amperian loop. Mu naught times I through is just usual Ampere's law. So this is the term that Maxwell added. So mu naught times epsilon naught times the derivative of the electric flux with respect to time. So this is kind of interesting because this derivative of the electric flux, well, it behaves like a current. And in fact, it's known as the displacement current sometimes. So the displacement current, which is epsilon naught times d electric flux dt. And you should remember, though, that it behaves like a current and can produce a magnetic field. It's not a real current, but it really is a key point and an important realization from Maxwell that a changing electric field can produce a magnetic field.